All right. As I said a few minutes ago, no, we're not having a quiz today because we just had one on Friday. We're likely to have one on Wednesday, though. Remember, turn your potential test questions by now. You're getting old hat at it. I still haven't printed more, but I still have a few up here. Does anybody need potential test question form?
Can I have one?
Yeah. You can have all the rest.
All right, I'll have all the rest.
Okay. So we're going to start with fluids today, but I want to finish talking about energy resources. So sources of energy. Remember I said last class, like 99% of our energy budget comes from the sun. And, you think about things, we use solar panels, sure. I want to get some for my house out in Colorado because we have lots of good sunshine there. And, it would be nice to be able to take advantage of that. But things you don't think about. I went to graduate school in the state of Washington, where we have Washington Water Power as the name of our utility, and the vast preponderance of electricity comes from hydroelectric generation. And so a lot of people would say, well, that's not solar power, that's water power. But if you think about it, it is driven by solar energy. You have sunlight that comes and hits water, like the ocean, heats it up, and that heated up water then evaporates and goes into the air, and then it rains somewhere. It's at a higher elevation, and it's the gravitational potential energy it has going from the higher elevation to the lower energy that we're using to create hydroelectric power. So the entire hydroelectric power system is actually driven by solar energy. Likewise, windmills. Windmills, of course, were driven by wind. It was very windy this morning. Our trash can blew away. Our neighbor's trash can blew over, so their trash flew across our yard. Limbs down everywhere from the wind. That's driven by the sun. The sun heats up some places. When it's hot, temperature is a measurement that tells us about the average kinetic energy of the molecules. Well, what is kinetic energy to you? It's a new term, generally speaking. So what does that mean when I say that temperature is telling us about the average kinetic energy of the molecules? The movement. Temperature is, in essence, telling you how fast the molecules are moving. Kind of a bizarre thought, right? Who thinks about that? This is hot, that means the molecules are moving faster. But it's true. It's what it means. And so when the sunlight hits things, the energy is absorbed and goes into making them go faster. That makes sense now that we have some understanding of energy. If I do work on something, I'll make it move. That means I increased its motion, increased its kinetic energy. And so when the air is hot, the molecules are moving faster. Those faster moving molecules then expand. And if you have colder over here, you'll have a higher pressure where it's hot and a lower pressure where it's cold, and you'll create a wind. And so the winds are created by solar energy. So solar energy, almost everything we do comes from solar energy. Like I said, there is a small fraction that doesn't, and that comes from radioactive decay. Now, something you may or may not know. If you dig down in the earth, you're going to go through the outermost region, which is called the crust, and that's everything we know. No human has ever drilled a hole that goes through the crust. But the crust is only, depending on where you are, between around 5 as a minimum to around 35 kilometers thick. 35 kilometers, that's go across the city of Lincoln, and you're close to the thickness of the crust at its thickest. So it's not very thick. We've never been able to drill down below that because as you go down, the temperature gets hotter. And if you have a drill going into hot material, your drill starts to melt. It becomes soft and then it snaps. And so that there have been lots of attempts to go through. But by looking at waves that we send through the earth, we are able to infer what it's like down there. Just like if you're pregnant, nobody sees the baby. I mean, you might see a little, there's the baby's hand every now, but you know what I mean. You can't say, "Oh, that's what the baby's face looks like." But how can a mother know what her baby's face looks like? Ultrasound. Because with ultrasound, they put the little transducer on here and it sends waves in, and then those waves reflect off of the baby, and then we receive back those waves and we can interpret what's in there. We do the same thing with the earth, except for it's not called ultrasound now. We're using seismic waves, earthquake waves, going through the earth, and they tell us that if we go down below the crust, we're going to have a very uniform region that's called the mantle, that's hot, essentially rock. You go deeper and deeper and deeper, and it gets so hot that it melts. We have the molten core. Why would it get hot? And by the way, if you keep going, you then have a solid core inside the molten core. Why would it get hotter as you go deeper into the earth? Reasoning ideas.
Because it's more dense? Or wait, no.
Density itself, density, by the way, is one of the words of the day.
I was thinking about something else. Yeah, because the molecules are moving more. And so,
There's so much pressure, it heats up the core. And that helps expand out the heat.
Okay. When the earth was formed, according to scientific theories, when the earth was formed, it formed by material falling in. If I take a ball and I let go, it falls, right? And its speed increases because its energy is increasing. Its kinetic energy is increasing, I should say. Well, that's what we believe happens when planets and suns and stars, whatever, form. Stuff falls in, so they move faster and faster, and so you have very hot when it's formed. And gravity is pulling things toward the center, and so during formation, the entire Earth would have been very hot, with high density in the center because of gravity. But then, of course, over time, the surface cooled because heat can escape into the atmosphere. Heat from inside the Earth has to slowly travel out. And so one part of it is the heat from formation. This is going with what you said, Bryson. The heat from formation of the Earth, from when the Earth had all this material that came together and crushed down, is still cooling off. So that's part of the reason that the core is much hotter. But it's only part. The other part is radioactive decay. We have unstable nuclei. We'll talk about atoms carefully when we get to chemistry, but the atoms, you can think of almost like you have something that balances. So I have this little eraser, and it's balanced here. And it's pretty stable, but if I hit it just right, boom, it falls over. Now it's more stable, right? I can't push it now and make it fall over again because it's in its most stable configuration. The nucleus of some atoms are like this in a somewhat stable configuration, but over time, something happens and they fall to a much more stable configuration. And when this fell to a more stable configuration, it made a sound you could hear. That's energy coming out. It was energy that went from the gravitational potential energy it had here into the sound energy when it came out. Nuclei are doing roughly the same thing. That energy is coming out and making stuff hot. And so that's the other less than 1% of the Earth's budget is the radioactive decay, which makes it hot in the Earth. So one of the sources of energy that's not from the sun is from using energy from the heat, the high temperatures in the Earth. So here's an example of a dry geothermal power plant, which is really cool, except for you notice that first step, the hydraulic fracturing. You've heard that a lot recently, probably. It's shortened to just call it fracking. Fracking is you put water in there, the material, and it fractures the rock. It's used in the oil industry to be able to break apart the rock and extract oil that's trapped in the rock. And through that, we now are producing a lot more oil in the United States. So I believe right now we're a net producer of oil. That is, we are taking more oil out of the earth than we consume in the United States and exporting. But this here is not used for water or for oil. It's for heating or producing electricity for a community. So you drill a hole, you fracture the rock down there to create a pocket where you can put in water, and then you cycle water. Now, you're not going to cycle water probably. This picture shows the water mixing in there and then coming out. It's more likely you're going to have water in that chamber and then pipes that go in, and you have kind of like a radiator where you exchange heat. So that the water in your pipes becomes the same temperature as the water in the outside. That's a way to keep contamination from your system. But then you have hot water that comes up, and you use the hot water's energy to produce electricity. So that's a way that's using the natural energy coming from the earth rather than the sun. When I was at PUC, nearby they have a geothermal plant where they have geysers. And there's so many geysers out there, there's a town named Geyserville. And so they use geysers to produce electric energy in the same fashion. Unfortunately, the geysers ran low on water. You don't have a geyser if you don't have water, right? And so they pump in treated sewer water to refill the chambers down here where you have hot material to heat the water. And then you start like, ew, gross, sewer water. But, you know. So that's another source of energy that we use. Now remember, energy can't be created or destroyed. That's a fundamental rule of physics. We can't create or destroy energy. What we're doing is transferring energy from one type to another. So here's a list of things that we like to use from sun. Photovoltaic panels, direct conversion of sunlight to electricity. Hydroelectric turbines, which is the water that was evaporated, went to higher elevation, rained, came back down, and then we used the gravitational energy, wind turbines, and even bio-based fuels. What's a bio-based fuel? Give me an example of a bio-based fuel. She said coal, which is true. What did you say?
Vegetable oil?
Vegetable oil, true.
Is there any non-bio-based fuels?
Not that I know of. Well, nuclear fuel is not bio-based.
Yeah.
But coal is, because coal used to be grass and whatnot that got buried and compressed and went through the coalification process. So it's bio-based. We generally don't consider coal or gasoline or oil renewable resources, even though they're bio-based. Why don't we consider them renewable? Takes too long. They are technically renewable, but not in any of our lifetimes. Whereas if you use what we call biomass is you find stuff and you burn it. You know, so out there in Colorado, there's trees all over the place. Tree falls down, you cut it up, you burn it, that's biomass. Or you cut down bushes and burn them. That's considered a good renewable resource because that stuff grows quick. Okay, I'm talking about this because it is important for us as humans to understand a little bit about energy and the energy we use. It's not an infinite resource. It can't be created or destroyed, but we have to convert it from one form into another form that we can use. And so being responsive about energy, you know, there are politicians who make stupid statements. You guys are probably aware of that, right? There have been some that said, I mean, if we use photovoltaic cells, we're going to use up the sun. Whether we use the solar energy or not doesn't affect the sun's production of it. That's just a false argument, right? The more solar energy we use, the better, in my opinion. But also be aware that nothing comes without its downside. Solar energy, what possible downside could there be? Well, it depends, first of all, on the type of solar energy plant you're using. One type of solar energy plant that is, I would say experimental, but it's been experimental inside college, is you have it, and then you have a big farm of mirrors around it. And the mirrors are computer controlled, so they will reflect sunlight onto that beacon. And so that beacon shines with the brightness of the sun. You look at that thing and you feel like you are going to be blind. You probably would damage your vision if you stared at it. Because you have all of the solar energy from a big area focused on this one ball that's just a couple meters in diameter. Well, that ball gets really, really hot. And they use a fluid that wouldn't be a fluid at normal temperatures, sodium, the metal part of salt. They pump it up there, and then it gets heated up. They pump it down. They use the sodium because they can store it overnight and stay still very hot liquid. And they use that for their transporting the thermal energy from the sun into a power plant. But of course, if it's hard to look at that beacon because it's so bright because of the sunlight hitting it, what happens if a bird comes flying by? Yeah, it gets cooked instantly. So there's a downside there. The birds, animals, often we interfere with them when we use these. You're going to change the local temperature somewhat with any kind of a solar power plant. And then there's pollution. A lot of people drive around with their electric cars. And electric cars are really good sounding. But there is an enormous amount of pollution that goes into making the batteries for those. Those batteries are made with things like rare earth metals. And so there's big mining operations to create those rare earth metals. And then there's all the processing that produces lots of caustic, deadly chemicals. And so you're causing quite a bit of damage to the earth by using a battery. And so you always have to balance these ideas. Nothing comes without a downside. Question, Grace?
What would be the downside of wind turbines?
Again, it's largely animals. Animals get hit by the blades and get hurt, killed. And also the noise disrupts them. So those are the downsides that I know of there. And of course, I'm sure you've heard of people like the Sierras Club saying we shouldn't have dams anywhere because we're disrupting the natural habitats of animals. I tend to disagree with them, but that is a downside. Okay. I'm going to pass over the hydrogen creation there and just get on to the new material because I spent 20 minutes already. Density. Grace used the word, and I said that is a word of the day for us. Density is mass divided by volume. It's how much mass you have in a fixed volume. It's not weight. If I take these two things here, this is 500 grams, this is 100 grams. Which one has more matter, the 500 or the 100? 500. The 500, because mass is a measurement of how much matter is present. Density is taking that mass and dividing it by the volume. Now, if you look at these two objects, which one has more volume? The 500. So the 500 has both more mass and more volume. Now, it turns out these are made of the same material. And so if you take the mass of this divided by the volume of this, you're going to find it's the same as the mass of this divided by the volume of this. They have the same density. This one has more mass, it's heavier, has more force of gravity, just because it's bigger, has more volume. At the same time, I could take these have similar masses. The eraser and this 20-gram mass. They're similar in mass. But the eraser has much more volume. Right? The size of this is much bigger. So for density, density is the mass divided by the volume. So the same mass with bigger volume means that this one here is less dense. So notice here it says lightness or heaviness of materials of the same size. It's actually, this comes from the textbook, but it's actually a poor statement because it can mislead you. If you don't have this clause, it's wrong, right? Because density is not about lightness and heaviness, but if they're the same size, then it will allow you to calculate that. So what is good here is a measure of how compact an object is. Something that's more dense is more compact. So let's think about densities of materials. What is something that to you think would be very heavy for its size compared to something else, compared to most other things? Okay, lead. Bryson goes with lead. Hannah.
Hosanna.
Hosanna. Hosanna beats him by a lot. Gold. Gold is far more dense than lead. So why didn't Bryson say gold? He's probably never held gold in his hand, right? Hey, look, here's a kilogram of gold. None of us have had that experience. But the gold is much more dense than lead. What else is more dense than lead? Now I'm not asking you because I don't think you're going to know answers. If you do, great. What else is more dense than lead? Mercury. That liquid. Mercury is a liquid at room temperature, but it's more dense than lead. And the most dense materials of all, if you look back there, we have the periodic table of elements. This is telling us all the different types of atoms that we know to exist. And so you have like the most common hydrogen. That makes up, what? By atoms, 91% of the atoms in the universe. By mass, something like 75% of the mass. Well, and when I say mass, I mean the mass of the stuff we know. Helium, lithium, beryllium, and so on. Things that are very important to us, things like carbon, because of carbon-based life forms. Oxygen, we need oxygen to process energy. Hydrogen, oxygen together make water, which is very important. Anyway, if you look on this, we have other things like, here's gold, Au, which is for the Latin word, but americium, Latin word for gold. Right next to it is mercury, Hg. I don't know what that stands for, it's a Latin word again. But the most dense ones, notice this is platinum. These are two very expensive metals, right? These here are the most dense ones, osmium and iridium. Just in case you need to know. Other dense ones, uranium is very dense. We use uranium in power plants, and so you have depleted uranium. Uranium that's not as radioactive as it used to be. Don't fool yourself, depleted uranium is still radioactive. But depleted uranium is not as radioactive, and they will use that in dumb bombs that are just made to go break things, because it's very dense. So for the same amount of uranium, you'd have way more mass than if you had put steel in there, or iron, or rock. So density is an important thing we use to differentiate materials, and there's the actual equation for it, mass divided by volume. The unit then, what is our standard unit of mass? Kilogram. Which is always tough because we tend to think grams instead of kilograms. What's our standard unit for volume? It's going to be meters cubed. Meters are distance, and since volume is length times width times height, if you're talking about a square rectangular object, it's meters cubed. So the standard unit for density is kilograms per meters cubed. We will also often list it in grams per centimeter cubed. The difference in these are I'll put 1 gram per centimeter cubed. If I want to convert that, now this is an important skill that we haven't practiced. If I want to convert the unit, I need to multiply it by something that's equal to 1 that will change from one set of unit to another. So here I have gram. I want to replace grams with kilograms. So I'm going to put kilogram on top because gram was on top. And I want to divide out the grams so that those will cancel. And then I need my conversion. How many grams are in a kilogram? 1,000. And so I have 1 kilogram is equal to 1,000 grams. And that will convert me from grams to kilograms. That's half of my conversion. For the other half, I have centimeters cubed on bottom. So where do I want centimeters in my conversion factor? I want the centimeters on top because I want them to cancel. What's the new unit I want? Meters. And the meters goes on bottom because that's what I'm going to replace it with. How many centimeters are in a meter? So 100 centimeters is equal to 1 meter. But then there's one more step. If you stop here, you're wrong. This has centimeters cubed. Let me fix that cube so it looks better.
Right, so you do 3 times.
Which I can do by just putting a cube on the entire conversion factor. So now if I look at this 100 cubed, that's 100 times 100 times 100. 100 times 100 times 100. How many zeros am I going to have when I do that multiplication?
Too many.
How many do I have in 100? You're right. How many do I have in 100? 2. So each time I multiply by 100, I'm going to add 2 more zeros. So 100 times 100 times 100 is going to give me a total of 6 zeros. So it's 1,000,000. So I have 1,000,000 divided by 1,000. Well, 1,000,000 divided by 1,000, 6 zeros divided by 3 zeros leaves 3 zeros. And so this is equal to 1,000 kilograms per meter cubed. So 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. Something that you should feel comfortable with, the density of water, the mass per unit volume, is roughly 1 gram per centimeter cubed. I say roughly. For a class like this, we would just say 1 gram per centimeter cubed. It varies slightly with temperature, but it's very close to 1 gram per centimeter cubed. So how many kilograms per meter cubed is the density of water? 1,000 kilograms per meter cubed. Oh, by the way, notice here I do have mercury has a density of 13.6 grams per centimeter cubed. So the density of mercury is 13.6 times the density of water. Same volume of mercury, 13.6 times the weight as it would be if it was water. Now a new term, lots of new terms. We just had density, now we have pressure. Pressure, dun, 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 dun. Yeah, you probably don't know that song, right?
Under pressure.
Yes. Yes. Okay, so pressure has to do with force. When I was a kid, I was very confused about this topic. You know, air pressure put in the tire and PSI. And I said, how many pounds of pressure? And I get really confused myself because it didn't make sense. You know, what's the difference in a PSI and an LBS? Does anybody know the difference in a PSI and an LBS? Well, the difference is pressure and force. So pressure is force spread out over an area. So pressure, first of all, it's going to have units of, force has units of, what's the standard unit of force? Newtons. And now we have area. Area is just length times width. So what should the units be if it's length times width? Meters squared. So pressure has units of newtons per meter squared, which we call pascals. So 1 pascal is 1 newton per meter squared. Just like 1 newton is 1 kilogram meter per second squared. And so we could put that together and say a pascal is also 1 kilogram meter per second squared divided by meters squared is equal to 1 kilogram per meter second squared. That would be another way of writing a pascal, but no one ever has, to my knowledge. Yes, Hannah?
What's a pascal?
So pascal is a unit for pressure. So we can just have 1 unit for pressure. So the SI unit, the standard unit for pressure, is the pascal. And if we say anything standard, right? Like in the United States, what would we use for distance instead of meters? Feet, inches, miles. The relationship between those, of course, 12 inches in a foot, 5,280 feet in a mile, I think it is. They seem like random numbers pulled out of a hat. The reason scientists don't use that is because They want something that's very simple relationships. So we use the metric system. We do things in meters and thousands of meters that we call kilometers or kilometers because we're Americans, and so on. So what's the unit that we use for force in the United States? I wish. Pounds. In the United States, we use pounds. And so if we were to use US units, I can't put equal because you have conversion factors involved, but our force is measured in pounds. The abbreviation for pound is LBS. What does LBS stand for? I think I told you early on. Libras. So Libras, like Libras holding the little scales to measure force. Well, actually, she's using a balance which would measure mass, but let's get past that. And then what do we use for area? It's going to be what we use for length squared. And in this case, it's inches squared. So in the US, we use pounds per square inch, which we generally write out as PSI. So PSI is pounds per square inch. And any logical person would say, shouldn't that have been L, for libras rather than pounds, since we use LBS for pounds?
So why does it say pounds per square inch up there, but then under the units it says pounds per square feet?
Because I took it from the textbook. But I've never seen anybody use pounds per square foot. I've always seen them use pounds per square inch, right? And that's what it says in your car tires. Maximum inflation, blank PSI. Minimum inflation, blank PSI. So pressure is a force per area. So pressure is not just force, it also has to do with area. So take as an example, let's say that I have this bowling ball, and I take this bowling ball and I put the weight so it's on my entire hand. The pressure is going to be the weight of this ball divided by the amount of hand it's in contact with, which is pretty low. But if instead I put it all on my pinky, the same weight on a much smaller area, what is that doing to the pressure? It's making it bigger. And so it would hurt if I just had this on my pinky, whereas on my hand, not a big deal. Why? Because it's a bigger area, hence the force is spread out, it's a lower pressure. And so the pressure is what I'm worried about for things like crushing. Also for cutting. I've talked about this once before. I'll talk about it in a different way. When I was in second grade, I had this huge crush on Sandy Pervorce. And so, the last day of school, by the way, she is the first girl I ever kissed, and I was shocked that she didn't realize I tried to kiss her. She said, that's unfortunate. Okay, so, when you're in second grade, things are meaningful. So at the end of school, you clean out your desk, right? And the teachers like to make it like a big party thing. You're like, oh, we're going to be missing each other, and here's all the fun we had. And so as we're going through, Sandy finds a pin. And she's like, watch this. And she puts the pin right here, and then she closes her arm. And I was like, ah! And then she opens it, and no damage. And so I'm Mr. Sandy Pervorce. What could I do? I had to do it too. And it also did no damage. How is that possible? I only did it because she did it. I'll tell you about me being stupid in just a minute. What?
Like this kind of fun?
No.
No, like a tap.
A pin you use when you're sewing to hem something up. You pin stuff up and then you sew it.
Oh.
How is it possible that it didn't do any damage?
I'd have to see it.
Well, I'm going to do it now. I have a little less fat here and a little more muscle. That would be a problem. my skin, okay, so you have the pinhead, it's pushing on here, and there's, of course, the skin is going to apply a certain force to it, it's going to apply force to the skin, and the skin deforms, and the force didn't get that high, and the head of the pin, even though they look sharp to us, was blunt enough that the pressure wasn't enough pressure to break the skin. Now, I would never do that again, nor recommend it. But then we go to, I think it was the next school year. I was up waiting at the front desk with the teacher, and she was talking to some other student, and I was bored. And there was a stapler. And I was like, I wonder how hard the thumbnail is. So I put my thumb in the stapler, and I push hard. And you know what? Eventually you do reach a high enough pressure. The stapler went right through it.
Now you're like in what, third grade?
Yeah. It was all science. Did you guys do things like this?
No.
Probably.
My mom won.
Okay, I just have to tell you about something nothing to do with physics of today. We had a cat. And I read that cats always land on their feet when they fall. I was a little kid. I didn't know any better. I was like, I must test this. Remember the scientific method. First thing is, you observe something interesting. In this case, I was told something interesting. And then the second step is to come up with a hypothesis. Well, I didn't come up with a hypothesis. I didn't explain anything. Remember, what are the three pieces the hypothesis has to have? Okay, it must make testable predictions. What did you say?
I said it best. I don't know. I don't know what I said.
I don't know what I said.
Why the observation occurred?
It has to explain why the observation occurred. And what was the last one?
Based on scientific ideas.
Based on scientific ideas. I had none of that because I was a little kid. I was like 8. But I was like, I don't believe it. I have to test and see. Let's say I was much more like Thomas. As a scientist, I kind of identified with the doubting Thomas, Got to see it to believe it. And so I took the cat, held it upside down from one step above ground level and let go. It fell on its back.
They're so mean.
I took it up 2 steps and did it again. I took it all the way to the top. At the end, I was dropping about 12 feet. The cat still came back to me. We're talking this cat may not have had a high enough IQ. But that's what science is about doing tests to see. Not about torturing animals. Don't do that. I feel really bad about it. Just to stay physics on it, how is this all possible? Well, here's something we didn't talk about yet. Angular momentum. We've talked about linear momentum. Things traveling in a straight line will have a momentum, and you'll have to put a force on there as per Newton's second law to change that momentum. Well, if you have something going in a circle, it still has inertia for every piece. Every piece wants to keep going in a straight line, and so they're going to go in a circle, but it's going to take a force to speed up or slow down the rotation. The rotational force, we call it torque. And so that's why, when things are farther out, they are going to be going faster as you rotate than if they're closer in. And so if you're rotating, you put things outward, because they're moving faster for the same rotation, your rotation actually has to slow down. And without something to slow you down or speed you up, if you put mass out, slow down, bring it in, speed up. And so the cats actually take advantage of this. They're like, let's say people who are doing ski jumping, when they're in the air, they're doing all kinds of gyrations. Why? Because they're manipulating the shape of their body and the rotation axis. Well, the cats do the same thing. They will start rotation, straighten out, get rotated back, and then bring their paws out. They're using physics at a really advanced level. The same level as those ski jumpers or divers and that kind of thing. Okay, it is physics stuff. Everything I talk about is physics. It's my life. Pressure is, when we talk about a fluid, we'll talk about water pressure, a fluid pressure. It's a force per area. if I have a bigger force on an object, what's that going to do to the object? If it can move, the net force is bigger, it's going to have a bigger. If I have an object and I put a bigger net force on it, what's it going to have for a result? Bigger acceleration. I didn't hear you say Bryce. A bigger acceleration. And so the more pressure you have on something, the more acceleration it'll have if it's free to move. So here's my demonstration for this. I always make a big mess with this one, but hey, if it even works, then it's fun. If it doesn't work, then it's not fun. So here I have a bunch of water. Put this out here and hope that at least 10% of the water lands in that. And I am going to let water come out of these two spouts. Where's the pressure going to be more, down here or up here? Down low. Why?
Because once the water gets lower,
Okay.
there's more volume.
Pressure is caused by the weight of the material above. Down here, there's more water above, hence more weight of that water above, hence higher pressure. So let's see if I can do this here. Well, see, one of them is hitting it. That's okay. Well, yeah. Stop.
No, you're good. Just, it was almost done coming out of the top.
Yeah.
Maybe you should have used the trash can.
Kidding me? It's all the way over there. Well, I
There's
guess
one
it's one
right
there,
there.
too. I caught about half of the water. She counts.
Like 10th of an inch of it.
You guys are critics. So why did the water down below shoot out farther again? Because of higher pressure. Higher pressure meant that you had more net force pushing the water out, hence bigger acceleration, came out faster. Now, this has some simple examples. Swim twice as deep, and the pressure due to the weight of the water above you is twice as much, which I always noticed with the pain in my sinuses. Yeah.
That's what I was going to ask. So the reason like your ears hurt when you're swimming down lower is because of the pressure.
Yeah. As you swim down lower, the water is pushing in harder and harder on your ears, and so you have this tympanic membrane that started with the air pressure outside before you dove in, and now you have more pressure pushing in than pushing out. If you're driving in the mountains, as you go up, there's less air above you. So what does that mean about the air pressure? It's lower. So that means the pressure outside is lower than the pressure inside, and your eardrums start pushing outward. Now you do have your eustachian tubes, which have as a purpose to allow equilibration between the outside pressure and inside pressure. And so when your ears pop, you're having a burst of air going through that tube. You have a question, Hannah?
You
Well, okay.
took the fun out of it.
I'm sorry, yes, it's more fun to ask and answer than to just, oh, yeah. Yeah, I did, but. So, what causes air pressure? I just said this. What's the cause of air pressure?
The less amount of.
It's the weight of the air above you. Remember, pressure is force over area. So if you have some area here and you weigh all of the material above it, then the pressure is going to be the weight of that material divided by the area. And so up there where our house is in Colorado, our house is at 9,400 feet elevation. I wake up in the middle of the night gasping for air sometimes. Got to get used to that. So because it's way up there, almost, getting close to 2 miles in elevation above sea level, the air pressure is only about 70% of the air pressure down here. Now, we still have 21% oxygen, 79% nitrogen. But with, roughly 2/3 the air pressure, for the same gulp of air, you're getting 2/3 the amount of oxygen. Lower pressure. Which there are a few molecules, in a given volume as well. In case you ever wondered why breathing up there is not quite as fun.
So, I went to Estes Park, and I spent the whole summer there, and I had never been above, I mean, I fly all the time to get here home, but I'd never been there in a consistent environment. And like, I went on a walk and I thought I was gonna die. Like, I was like I barely walked out of the house, and like I had to have lots of medicine because like the headaches, terrible.
Yeah,
If you don't drink water, it's terrible.
there's elevation sickness that, depending on the elevation, a lot of people are going to get. So where we live, I think 40% of people are going to get elevation sickness, and until you get used to it. What?
At 9,000 feet,
Yeah.
it's bad.
So then it increases when you get to 10,300.
Yeah. That's where you live? Okay. Well, yeah. So we already did this example. Now, I'm going to finish just on something that I talked about before that has to do with air pressure. When we're talking about the forces on things, I mentioned, and here's a force that we're not really aware of, the buoyant force. Air pressure is pushing in all directions on me. In fact, I got to give another example. This is one of my favorite demos, assuming I find it, of course.
No, so close to the bottom, like this is a color. They were like down there. But I would talk to someone else, which is kind of close.
I love Estes Park. That place is expensive though.
I am a Colorado.
Okay, I didn't see it, so I'm not going to waste the time in looking for it. But we have air pressure pushing all around us. The force due to air pressure is always going into the surface. So if you look at, let's say, this monitor here, what direction is the force due to air pressure on this surface? It's going straight in. What about on the top here? Straight in. Here, in, right? It's in everywhere. So if you look at your body, I put my hand out. What direction is the force of the air pressure on the top of my hand? Down. What direction is the force of air pressure on the bottom of my hand? Up. Well, the area of the bottom of my hand is the same as the area of the top of my hand. The air pressure, how would the air pressure on top compare to the air pressure on bottom? Very close to equal. Because if you come out here, now the pressure is the same here as it is here. So if I come out here, I have a difference, my hand's kind of a fat hand, so I have a difference of about an inch in elevation. Well, pressure does not change very much in an inch. So equal is correct. So my hand doesn't feel like it's being pushed around by the air pressure. But the fact is the air pressure on the bottom is slightly higher because there's slightly more air above, and thus it's pushing up a little, which we call buoyancy. So now we take my whole body. Believe it or not, there's air under my feet. I do not have a seal between my shoes and the floor. If I did, well, that's where my demonstration would have been awesome. I wouldn't be able to lift my feet. If there was not air under my feet, I couldn't lift them. They would be stuck to the ground. Yes, it would be a suction. That's just a big suction cup for my demo. So I have air underneath me pushing me up. I have air on top pushing me down. What about sideways? Is there air pushing me on my chest?
Yes.
What direction?
And like,
Okay. What about on my back? Pushing forward. Now those are the same elevation, so those are definitely going to balance. So there's no net force pushing side to side because the pressure is the same elevation. But there's more pressure down below than above, so there's a net upward force that we call buoyancy. This is what we're going to study in the lab this week, is the buoyant force. If I go into something that's more dense, what's more dense than air? Pretty much everything. Water is about 800 times more dense than air. So if I were to do the same comparison in water with 800 times the density, it turns out the pressure differences are 800 times bigger. And so in that case, there is a significant difference in the pressure down at my feet compared to the pressure at my shoulders. And so there's a net upward force due to the water because the pressure is higher at my feet than it is in my head. And that's why we float. All right. Have yourselves a great day. And let me try to keep these people from falling and hurting themselves.
Dr. Love,
Yeah.
what was the name of the girl that you did the thing with?
Sandy Horse. It's now Sandra Kreitzer. Well, the Facebook name is SAN space DED. And no, it is not a good question to say, who did Dr. Webb have a crush on in second grade?
No, that's not my question.
Good.
It was one of the answers.
That was my question.
Wait, what do you mean one of the? Oh, for that?
Or yeah. What's part of my answer?
Oh, like it's a funny answer.
Mom know this story?
Hmm?
Does Amy know that story?
I don't know. Doesn't matter. If she does or if she doesn't, you can tell. I don't care. Oh, I better turn off the recording.
Thank you, Ryan.
You can always listen to my lectures.